Guys, welcome to Quantum Clarity Lab, a channel where we learn physics and mathematics using first principles and not memorization. Okay, so let's get started. So we have our first question for today. So let's read the question. A stone is attached to an inextensible string of breaking stress rho naught and cross-sectional radius r and length L. So we are given a string. So let's write what's given. We are given a string of length L and breaking stress rho naught and cross sectional radius r. Okay, so string is fixed at one end, mass of the stone is m, and a force acts tangential to the string such that stone moves in a circle. So this is a question of circular motion and provides tangential acceleration of at is equal to alpha e to the power beta t. So what can we observe about the tangential acceleration? That it is not a constant acceleration, it is changing, it is exponentially increasing. So where alpha and beta are constants, given that the stone starts from rest, find the time after which the stone breaks off the string. So we are asked the time. So let's try to understand this question better. We can start by drawing a diagram. So let this be the pivot point and we'll draw the string. So this is our string. Let this be our stone. So first thing we'll do is we'll make this a free body diagram. We'll note down all the forces on the stone. So since it's a stone which is connected to a string, it will have a tension force. So this is our tension force, and then it is given that it is moving in a circular motion. So we will have this tangential force or acceleration. So let this be our tangential acceleration. And then we have our velocity. We know in circular motion the velocity is always perpendicular to the centripetal force or centripetal acceleration. Okay, so this part is clear. Now we'll get back to the question. So now the force is acting like this, and it is causing an increase in acceleration, and that too an exponential increase. So if we try to note down the exponential function, it is alpha e to the power beta t. Okay, and the question asks us to find the time after which the stone breaks off the string, and we are told to ignore gravity. Okay, so why will the stone break off the string? Okay, we'll observe this. We'll get a closer look of this string. This is just a crude diagram of a close-up of a string. So this is just zoomed in part. Let this be our stone. So the string is attached to this stone. There's no gap here. Anyway, so this is the direction of our tension force. So if we observe, tension force is the force which is giving it the centripetal acceleration, and This is our radius of cross section. Okay, so we can observe that tension force is the force which is giving it the centripetal acceleration. So T is equal to m into a centripetal, and we know centripetal acceleration is v square by, what is the radius of the circle? L, the length of string. Okay, so we have mv square by L. Now if we observe, when we talk about this velocity, it is tangential velocity, not radial velocity. So, but the tangential velocity is not constant, it is increasing along with acceleration. So as a result of that, the tension in the string will increase, and after a point when the tension becomes greater than T max, which is the maximum tension that the string can hold, the string breaks. Okay, so we'll find the T max. So what is given to us? Yeah, it is given to us that the breaking stress rho naught, and we know breaking stress is equal to maximum tension that the string can withhold by area of cross section, that is pi r square. So from here we can get the T max to be rho naught into pi r square. Okay, so we have our T max. So let's substitute the value of T is equal to mv square by L. So our boundary case is when T becomes equal to T max, that is when the string will break. So we have to find at what time T becomes equal to T max, and we know T is equal to mv square by L, and our T max is rho naught into pi r square. So from here we can get what is the maximum velocity before which the string will break. So we, by taking all the terms on the other side, square L by m to the power half. Okay, so this is our Vmax. Sorry. This is our Vmax. Okay, so since now we have got Vmax, our question is reduced to at what time will we get Vmax. And one more observation that we can see from the question is that given that the stone starts from rest, so our initial velocity condition is also given. So V0 is 0. Okay, so how do we find the velocity or the time at which the velocity will be max? So we'll do that using calculus. So we've been given the acceleration equation. Tangential acceleration is equal to alpha e power beta t. So we know acceleration is equal to dv by dt. We just take dt on the RHS, dt on the RHS and integrate. We know our initial case v0 is 0, so at time t equal to 0 we have velocity to v0, and at time t we have Vmax. So this will be v, integral dv is v from 0 to Vmax, and we can take alpha to be constant and outside, and integral e to the power beta t is e to the power beta t by beta. Our limits are from 0 to t. So upon solving we get Vmax minus 0 equal to alpha by beta e power beta t minus 1. Okay, so now we have to isolate t from this. So our Vmax is, I'll just write it down on this side, rho naught by r square L by m to the power half, that is equal to alpha by beta e to the power beta t minus 1. So all we have to do is solve for t. So our e to the power beta t minus 1 will be beta by alpha into rho naught by r square L by m to the power half. So taking 1 on the RHS and taking log, we have beta t equal to 1 plus ln of 1 plus beta by alpha into rho naught by r square L by m to the power half. Now all we have to do is take this beta on the RHS. So we have t is equal to 1 by beta ln of this big term. So that is our final answer. So how did you like this question? Thank you so much for watching. Please let me know in comments if there are any feedbacks, and thank you.